Okay. I thought, being that it's Halloween, I might start with a bit of a demonstration. So can you all look back here?
Is that a demonstration?
I use the chocolate.
No, I'm using it right now.
Let's see what I've got here. Okay.
Bruh, I ain't getting
Well, what fun would it be if it weren't? Yes. Yes, she's on her way. Can she wait just 2 minutes? Okay, thank you. Okay.
Oh my God.
Okay. So I've got some chemicals here. And I want you to make some observations about each of these. So now they're really different. So we want to make sure we're paying very close attention. They're all very different things, and that's very different. So could somebody describe this for me? Not the glass, but the substance we're talking about itself. The substance I put inside. It's transparent. Good. You can say transparent. You can say clear. Very true. What else? Yeah, it flows pretty well. So its viscosity is low. Good. What else do we got? Yeah, it's not solid, so it's definitely gonna be ductile. What color is it? Yeah, it's clear. In fact, it's not only clear, it has no color. Because it could be clear and say blue. You think like Kool-Aid, you can see through that, but it's blue, right? So this is not just clear, though it is clear, but it's colorless, right? So it's a clear, colorless liquid. Okay. Now, what about this one? Now is it the same stuff? Okay, we'll have a different bottle. Like it's got different letters on it. It's got all different letters and numbers, and Mr. Smith signed it, and there's a date on it. And this one's got different letters and different numbers. But can we see any difference between these?
Other than there's more in that one.
Yeah, there's more in this one. Good. So they have different shape and volume right now. But in terms of the substance itself, its idos, its perfect form, they're pretty similar. And then, just to make things super complicated,
translucent.
yeah, and the translucency just comes from the crappy plastic bottle. All right. So if I put this stuff's very expensive, so I'm not gonna pour it in like this. But if I did, you'd see that it's just the same. Now, I want you to pay close attention. Okay, listen. Shh. This is pretty dramatic. All right. So it's just,
I don't want to see it.
Okay. I'm gonna put in 1 drop.
Whoa.
What do you
Oh my
mean?
God.
Oh no.
They shouldn't do that all.
Oh no. Good. Oh. Wait, did you see something?
No.
I swear I saw something. Let's look really close there. Let's look really close there. I swear I saw something.
Oh, I see something.
But it's gone. It's gone. What happened?
It's a thing.
I don't know either.
Oh, it is.
What turns purple?
Why is it doing that?
What do you think? What do you think would happen if I put this and that?
Do it.
Oh,
It's gonna turn really, really purple.
Boom.
Oh, good.
Oh, ew.
Chemical reactions.
Oh, poor you.
You need
Will it go clear now?
Turn back way.
What? That's hot.
Yeah, it is.
What the heck?
It's gone.
And,
That one's canceled.
We're done.
The other one.
okay, so,
It's about.
oh, there you go. So what is going on here? Now, by the way, what if I put a bit more of this back in? I'm not even gonna do much. Let's do just
What? What? What is that?
we'll get there. There we go.
It disappears if there's not enough.
So what is happening now? Obviously, what must be happening?
The reaction.
No.
Yeah.
You have to-
That's right. Now, I want to be clear, and this is a safe product for the drain. Not everything is, so don't get in the habit of just pouring things down the drain. This one here, for reasons you'll understand in a few weeks, I'm actually just making salt water.
Pink salt water.
Sorry?
Pink salt water.
Yeah, so neither of them starts off as salt water. If I drank just this, I'd get pretty sick. If I drank just this, I'd get pretty sick. But I just want to show you that these two chemicals alone don't do anything. There's one of them. Nothing, right? No reaction whatsoever. So it's not two of them that works. It takes a combination of two of them to work, and a third one cancels it out. Interesting, right? Interesting. So if I put these two together, I could make it pink, but it would only ever be pink. If I put these two together, nothing will happen. That make sense? If anything, it says NaO, but it's a sodium hydroxide. It's a little better. Yeah. So, let me just hold it around my hands. But I want to talk about this, because we're going to do a bunch of different reactions over the next bunch of days, and we want to make sure we know what we're looking at. A little less fancy. There we go. Let's look up this way. Okay. Oh, yeah. Thank you. Okay, so today, in a unit about chemistry, today's the first day we're really going to talk about chemistry. Now, here's the great thing. I'm a little biased. I'm a chemistry teacher. But what I'm saying is true. What you're learning about now is more important than anything else you learn in school. All right? So, here's the deal. Chemistry is like magic, but it's real. And that makes it better. All right? Which means chemistry class is basically Hogwarts, but it's real, which makes it better. So, now, Einstein said that chemistry is learning God's thoughts, right? Like that's, and that's not meant to be a religious statement, but rather what it's saying is when you study chemistry and when you study physics, it's not the same as biology. Biology was studying living things. Does that make sense? So when you study biology, you're studying certain things that exist inside the universe, and we're learning about them, which is great and which is important. But chemistry and physics are different. Because if, and we don't know this, but if there is some alien planet where alien things live, their biology may be nothing like ours. The biology we learned here may do nothing to tell us about how the biology there works. Does that make sense? They could have been life forms that came to be in a totally different way. They could look nothing like us. They could behave nothing like us. The living things could work totally different than us. They might not learn about photosynthesis because they may not have plants that do photosynthesis. They might not have oxygen in their atmosphere or carbon dioxide. We don't know. But here's what we do know. If those little green aliens studying chemistry somewhere, they're learning exactly what you're learning, no matter where they are. Because chemistry and physics doesn't describe things in the universe. They describe the universe. They describe how the universe itself works. All right? So they describe how everything around you is made, how everything around you works. And that's pretty fascinating stuff. So chemistry can be tricky sometimes. It can be a tricky subject. Ms. Haig, you find from time to time that chemistry is a tricky subject? Yeah, it is. There's no getting around that. But it's a fundamentally rewarding thing to study because it shows us how the universe around us works. You know what, I was going to try and come pick that up for you, but with my big whip there, I will just end up hurting people. So I'm going to leave you to it. I apologize.
Good luck.
I was trying to be conscientious, but that wasn't happening. So today we're going to talk about a substance's chemical properties, okay? Not its physical properties, but its chemical properties. Now, the difference between a physical and a chemical property, what do you think that is? What do you think? What happened over there? Yeah, so I took a bunch of chemicals there and I mixed them together and I made new things. Does that make sense? When we started, that pig substance didn't exist. It didn't exist. I made it. I made it right there by mixing different chemicals together. Shh. And then when I put the other chemical back in, I made it stop existing. Does that make sense? I created something and then I destroyed it. All right, so in chemical changes, chemical properties tell us how substances tend to change into other substances. So we're going to describe that chemical reaction back there. And I took two things and I made them into something else. And I took that thing and I made it into something else again. The fact that it wants to do that is a chemical property. Does that make sense? Over there, some things will react together to make that pig substance, but different combinations won't. Does that make sense? Chemical properties tell us what kind of chemicals like to be changed into what different kinds of things. If you want an analogy, if I was trying to build a house, there's some things I can use and some things I can't. I can build a house out of wood. I could build a house out of brick. I could build a house out of steel and concrete. I'm going to have a tough time building a house out of marshmallow, right? It's not going to work well. Does that make sense? So it doesn't mean that there's only one thing I can use, but some things will make a house and other things will not make a house. That, again, that's just an analogy, but does that kind of make sense? I hope. So a chemical property is all about how something likes to changes. Now, what's the difference between a chemical change and a chemical property? The actual chemical change, in an actual chemical change, a new substance is made. By the way, does anyone know the word we have for that? When we take a chemical and we actually make it change to make something new. There's a word for that. We call it a chemical. Very good. That's right. So we call this a chemical reaction. That's what the next page is all going to be about. So now that we know that, we can go back up here and we can say a chemical property is how a substance likes to react. Yeah, of course. Yeah, absolutely. So, what's an example of a chemical property? Well, I could say What's that word mean? Flammable. What's that mean? It can catch fire. So, for example, what's something that is flammable? Good. Wood is flammable. What's something that isn't flammable? Yeah. Well, metals can be actually, but at very high temperature. Tomorrow, actually, we're going to burn a little bit of metal. Though in general, we think of you being right, but at a certain temperature, they will ignite. Yeah, water. Oh, sorry, Thursday. That's right. Water is not, right? Water will not catch fire. Try though you might. It might evaporate into steam. It's not gonna catch fire though, right? So again, that description tells me whether or not something likes to react or whether it doesn't like to react. It's how it likes to change. Wood, when you heat it up, likes to change by catching fire, and that makes new things, and we'll talk about that. Water, on the other hand, when you heat it up, does not like to catch fire and change into those same new things. Doesn't happen. What else would be a chemical property? A kind of reaction that things can undergo. What do you think? Yeah. Do you know what the word for that is? Corrosive. Acidic kind of means the same thing. Oh gosh, can I spell this? Okay. All of those letters may be single or double. For all I know, there's 3 of them. I don't know. That's not right, is it? No, not 2 S's, but 2 R's. I think you're right.
Oh my god. Yeah, there's only 1 S.
But 2 R's.
Yes.
It's not like gross.
It's not corrosive. Yeah, you're right. Okay. So corrosive. Okay. And again, corrosive. Acid is corrosive. Yeah, wood is not corrosive. Good. And again, this is describing a type of reaction that things like to undergo. Yeah.
Another one for like properties.
Yeah.
Explosive.
Ah, yeah. Is it explosive? All right. Gunpowder is. Stones are not. All right. If you come across an explosive stone, get away from it. Does this make sense? So each of these, and we could keep, do you have one more? Oh yeah, absolutely. Poisonous. That's talking about a chemical change. If you put a poison inside your body, it will react with things in your body and kill you. That causes a chemical change. If you put something that isn't poisonous in your body, it won't. So rat poison is corrosive, or is poisonous rather, and potato chips are not. Unless you get all dressed chips, in which case, come on. Right? Like, come on. That's false. That's just not true. That was creepy. That was creepy, and that, Richard, is why I'm not going to fail you, because I don't want to have to teach you again next year and be told things like that, but I'm going to make it close. No, I'm kidding. I'm going to fail you. And then I'll retire. Then I'll get fired for saying things like, I'm going to fail you. Hi, Miss Sergeant. So, here's what I'm talking about. How do we know if a chemical change has taken place? How do we know? What are some things we might expect to see if a chemical change has taken place? So, okay, well, exploding isn't really something we see. It's a chemical change. So if something exploded, what would we see? Or experience? Okay, good. So, we might see smoke. Smoke is a good sign. And I'm going to say this, or other gases released. Now, does that mean that every time we see smoke, it necessarily is the result of a chemical reaction? I mean, maybe if I wanted to, I could have collected a bunch of smoke in a balloon and then released it later. That's not a chemical reaction. That'd be a stupid thing to do, by the way, but I could do it, right? Or if I say gas released, if I open up a gas canister, I'm releasing a gas. Does that mean a chemical reaction has happened? Not necessarily. So listen, those are good signs. It doesn't definitively mean it's happened, but it's a good hint that it may have happened. Does that make sense? If you see that, it doesn't mean, yes, I know a chemical reaction has happened, but it means one likely has or may have. Yes?
Change physical appearance.
Sure, good. Let's be even more specific here. Let's say a change in color. A change in color is pretty much, is it a given? Yeah, a change in color is absolutely a given that a reaction has happened. Something cannot change color without changing what substance it is. It has to change color. So that's a good one. Somebody said a change in smell. That's good. Now be clear. That doesn't mean that it smells. It means that it changed in smell. Does that make sense? Just like it has to be a change in color. You can't say, hey, I see something blue. That's a chemical reaction. That doesn't make sense. But if I see something that used to be clear turn blue, that's a chemical change. Does that make sense? What else might I see or experience? It doesn't have to be see necessarily. I mean, somebody mentioned an explosion. If an explosion happens, what do I observe? Okay, so let's talk about fire, because fire is a few things at once. What is fire? Fire makes
Smoke.
Yeah, we talked about smoke. Good. What else? Sure, that's a gas released, definitely. So that's good. We've got that covered. Heat. Okay, so heat released can be a good sign. What else does a fire make? Or an explosion. Explosion is fire, so that's gases and smoke and heat. Let me ask you this. Does a blind person know that an explosion has happened? What is it? Light. Very good. What else? If I'm blind and deaf, I can't. Oh, I meant to say. I keep. Are you? Oh no. Do you want to go to the washroom, sir?
Yeah.
Okay, you don't have to ask me for situations like that, by the way. You can just tell me that you're going. Thank you, sir.
Oh, it's just gonna bleed out.
Yes. Yes, very good. Now again, does everything that makes sound involve a chemical reaction?
No.
Of course not. But sound can be a sign, right? Explosions are loud. Yes. Yeah, very good. We could have motion as a result of a chemical reaction. Your car moves as a result of chemical reactions. All right, you put gasoline in the engine. That gasoline is injected into a cylinder. It's mixed with oxygen. It's compressed, right? A spark plug fires. That gas explodes, right? It produces lots of carbon dioxide and water and a lot of movement. It forces the piston up. Then your exhaust valves open and let the gases out through the exhaust manifold into your tailpipe. And that piston moves around, and then the exhaust valves close. Yeah. The exhaust valves close, the intake valves open, let more gas in, and the process repeats. Guys, yep. Guys? Yeah, definitely. So like shrapnel and things like that, which is more motion for sure. The other thing I would say is this. We could sometimes see, and I actually should have had this one. I should have had a demonstration for this. I'll have a demonstration for this tomorrow. We could take two liquids. How about when I say tomorrow, you internally know that I mean the day after? Okay, so rather than repeatedly having this conversation. So, and I will make an effort to say Thursday. But if I mix two liquids and a solid forms, that'd be a pretty good indication, right? That happens. And that is called, this is a big word, a precipitate, which interestingly means the exact opposite of what that means when we're talking about weather and ecology. In chemistry, a precipitate means a solid forming from liquids.
Did you survive?
That's right.
I'm glad. That is serious commitment to Halloween, might I say.
It's part of his costume.
Yeah.
It's part of my duty.
Oh, I was going to put this in the space below. Whoops.
Whoops.
Well, that's okay. That's okay. All I was going to put in this space is the sentence, we look for specific changes. So if you really want to write that somewhere, you can.
I'll
So-
just switch them and then put it in.
All of this list was going to be down here. Whoops. Sorry about that. It's okay. I think you guys have got most of the major ones. So rather than go nuts, we will see a few more. We'll see a few more signs as we go. And as we go through the unit, maybe we'll come back and add those to this note. But this is a good list. So the last thing I want to say is this. If we go to the last page, there's another very important trait, which is this. All chemical reactions can be reversed. What do I mean by that? What did we see back there? Yeah, I made a new chemical. I made that pig substance. And then, just by adding one more thing, I unmade it. I actually moved back to what I started with. All chemical reactions can be reversed. Now, that's not always practical. Not always practical. For example, to reverse an explosion completely, I would have to collect all the stuff it makes. I'd have to collect all the smoke, collect all the gas. Am I practically speaking going to do that? No, but I could. That's the point. If I could collect everything, they can all be reversed. And I want you to think of what example of that do you already know? What example do you already know of a reaction that can be reversed?
Noah or no A.
Not that one. You're right, that one. But from unit 1, from our previous unit, what reaction do we know of that can be reversed? Okay, that one too. I'm not going to use that example, though you're right. The big one. What do plants do again when they get light energy?
Oh.
They take carbon dioxide. Well, plants take carbon dioxide. How many carbon dioxides does a plant need? And what else does it need? 6 what?
CO2.
It's got 6 CO2 and?
H2O.
Yeah, 6 water. And it makes,
Plus energy. Plus
yeah, you're right, plus energy. Gives us,
glucose.
yeah, which is what?
H12O6 plus O6.
And how many, plus O2, and how many of those?
Are we writing this? 6O2.
Yeah, absolutely. This is photosynthesis, right?
And then you switch it, it's like
So there's a chemical reaction. And what can, and cellular respiration does what? It does the exact opposite. Thank you. So any chemical reaction can be reversed, even ones you might not think of. Like say you take a log and you burn it on the fire. We may think, oh wow, that's a reaction that can never be reversed. But in fact, I can guarantee that reaction will be reversed. When will that reaction be reversed? So I take a log, I put it on the fire, and I burn it, and the log's gone. Why will it be reversed? To get bigger and make make logs, right? Like basically, does that make sense? So if you think about it, even chemical reactions we don't think of, you know, like you burn gasoline in your engine, it's going to take a long time, millions of years, but eventually that gasoline will be absorbed by people and trees and plants and animals and all these things, which will die and which will decompose in the ground, and some of which will be covered up, and some of which will be compressed and turned into new oil in the ground. That reaction will eventually be reversed. Now, to reverse burning fossil fuels takes millions of years. To reverse burning a log takes a couple of years. But it's the same idea. All chemical reactions can be reversed. Yes. Okay. So it's not always practical, but it is always possible. Okay, again, if I like, you know, my car that burned up, realistically, it is unlikely that's going to, all the pieces from that are going to get collected and turned into a new car. Though some of it, you know, I'm sure they recycled some of the scrapped hulk of it into like recycled metals, which could become a new car. But you know, some things are more practical than others. I'm pretty sure the books in the front of my car are not becoming new books anytime soon, to say nothing of my money, which was gone. And that was back before like money was all plasticky, so it won't even have a chance to be made into money again now because like we've changed how we make it. I want to note a couple things that aren't chemical changes. A couple things that are not chemical changes. That might seem like chemical changes. What's something that might seem like a chemical change? Let's say I started with water. What could I do with water that might make me think I've seen a chemical change? Sure, that probably would be a chemical change. I want to stick just with this. Yeah. I could boil it to make steam. Is this a chemical reaction? No, because what is water? Water is H2O. It's two hydrogens stuck to an oxygen. We'll talk about that. What is steam? H2O. Steam is actually just water. What's particle theory tell me? What's the only difference between the steam and the water? Yeah, so the particles that make up the water, what can you tell me about those? Back to particle theory, yeah. That's it. It's the exact same particles. When they're steam, they're far apart. When they're water, they're held kind of loosely together. Hey, what else could I do with that water that would not be a chemical change? Yeah, I could freeze it. And if I do that, I would get ice. We actually do science students a disservice by giving these different names. The truth is that these should be called water. Like, really what we should call these are liquid water. We would call this solid water. Now, mind you, if you like went to the convenience store and said you wanted to buy some solid water, they'd look at you like you had 6 heads, but there you go. And this should be called, yeah, what's the adjective form of gas? You could call it water vapor, for sure. So that'd be fine. Or we could say, what is the actual adjective form of gas? Gaseous. Gaseous. Yeah, if you want to use gas as an adjective to describe something, you say that it is gaseous. Gaseous. That's right, I can't spell, what couldn't I spell today?
Corrosive.
I can't spell corrosive, but I can spell gaseous. Yeah, it'll either be pronounced gaseous, but usually you'll hear people just say gaseous. It's like how people, nobody says Toronto, they say Toronto, right? You can totally tell, you can tell somebody who isn't from around here because they say Toronto, right? And we don't. We say Toronto, Toronto. It becomes a 2-syllable word, right? We say Toronto. Maybe a W though. Toronto, right? That's what we say. Right? It's like, you know, it's like comfortable. Now, of course, that's not the word. What is the word?
Comfortable.
Yeah, the word is comfortable. Comfortable. But we don't say that, right? We say, actually, I do say that, and everyone makes fun of me for it. But most people, normal people, say comfortable, right? So anyway, so we normally say this as gaseous. Gaseous. Okay. So that is one thing. This is not a chemical change because we only have a chemical change if something what? Yeah, if you have to have a different substance. There's no new substance, no new particles here. It's the same particles, and that means it's not a chemical change. Even though it looks like a chemical change, right? Because we said if a solid forms or a liquid forms or if gases form, that's a good sign that chemical change has happened. But the one exception, if all you're doing is freezing something or boiling something, that's not a chemical change. What else is not a chemical change? Here's one that's really easy. This is obvious. If I had nails and I put them in water to make my patented nail water, here's what ails you. Is that a chemical change? No, because what did I have when I started? Nails and water. And now I have nails and water. They're just in the water. So this is not a change.
After a while, the nails by the road.
That would be a chemical change, but this is not. Now, on the other hand, what about salt plus water? What do they become? Salt water. Now, this one's tricky because this is what kind of mixture? Yeah, this first one, this is a solution. This one was, what do we call this when we mix two things and we can still see them? Very good, mechanical mixture. But still, when I have salt water, I still just have salt and water. Yes, they're together now. Yes, they're a solution. Yes, it's one phase, but this is still not a chemical change. In all of these cases, I haven't actually made anything new. Does that make sense? Salt water is not something new. It's still just salt and water. And by the way, I could easily separate them. How do you separate salt water? Yeah, you just let the water evaporate off, or you can even boil it off if you're in a hurry. And you'll have salt and water again. No chemical change. At no point did it change. So there you go. You've got some homework here. You have the duration of time remaining, 10 minutes. Listen, I understand it's Halloween, but are we meeting tomorrow? No. So do I expect you to do this tonight? No, I don't. Here's your task tonight. I want you to eat lots of chocolate. Okay, yeah. My advice tonight, I have to do schoolwork tonight, but you don't, so I encourage you not to. But before Thursday, this needs to be done, and Lauren's going to check it. And you can start making some good progress right now. Get to work. An answer on lined paper. There's clearly not enough space on this page to answer, and I will not read your answers carefully written in tiny little letters next to these questions. Get a separate piece of paper and write on it. Sorry, what was that?
Yes.
Thank you.